All right, welcome back. Let's continue our discussion of anti-differentiation of composite functions via substitution. All right, now, so the previous examples, basically we had all the parts we needed, or maybe we're missing just a constant, but we basically can use what's called pattern recognition to anti-differentiate. That is, we can simply observe that, okay, it might take a little bit of, critical thinking and, know-how, but like, all right, there's a derivative evaluated an inside function times the derivative of the inside function. With some practice, you can get to be adept at that practice. But there are times where you just don't see it. Maybe you just don't see the chain rule, or maybe you're just having a hard time with that. I understand that. I remember this topic being very difficult for me when I took Calc 1, 15 years ago, I guess, at this point. Okay. So we're going to talk about a new way that's called, a change of variable, or a lot of times it's called U substitution. You've heard me say that term a lot of times, substitution. But I guess it gets its name from when you change the variable, you substitute the variable, the original variable, maybe x or t or whatever, for a new variable. And usually we use u. We call it U substitution. Before we do that, though, I need to review something, or actually bring a topic up. I don't usually bring much attention to this in the previous parts of the class because, to be honest with you, it's a topic we really gloss over in most Calc 1 classes, but it is something you need to know now. It's super easy. I should say this. If you treat the topic with maybe what it deserves, it's a very in-depth topic. But to get what we need to solve integrals via substitution, via U substitution, we can just scratch the surface a little bit. And the topic is differentials. Okay? Again, differentials can get very deep. We're just going to get what we need. Okay, and here's what I need you to know. Let's look at a couple columns here. Let's look at some functions. Let's look at the derivative of those functions. Oh, did not mean to do that. Derivative. And then the last column, let's look at what a new thing called a differential. Differential. All right, let's look at an easy one. Oh, let's say y equals x squared. Now, of course, what's the derivative? We know that the derivative we could say is y prime, or we could say, in fact, let's do something better. We'd also know that we could say that's dy dx. That's like the Leibniz notation. Dy dx. Oh, not dz. Why did I put a z there? Dy dx equals 2x. Here's what differential is. For what we need it for, we can say it's a new notation. And the differential is simply dy equals 2x dx. It looks like what you're doing is multiplying both sides by dx. I promise you that's not what you're doing, but it looks like that's what you're doing. Okay? And so the differential is simply dy is the derivative times the variable d times the d variable, what you're differentiating with respect to. Okay, here, let's look at a couple more examples. Oop, I erased too much. What about y equals sine x? Okay, what's the derivative? We could say dy dx is what? Cosine x. In differential form, we would say dy equals cosine x dx. That's the differential form. Okay, one more. Let's look at y equals the square root of x. We've done that derivative a ton. Now, I'll spare you the details. We could say dy dx. Now, you should probably have this memorized. 1 over 2 square roots of x. If you apply the power rule, that's the derivative. But if you want to write it in differential form, you could say dy equals 1 over 2 square roots of x dx. Okay, the differential is just a different form, and it's going to be important for us because notice we do have all these dx's in our anti-differentiation exercises. Now, previously, we've just referred to that as the variable of integration. That's all we've done, and that's been sufficient thus far. But going forward, we need to pay more special attention. Why? Because we're going to have a change of variable. We're going to change over from the original variable, a lot of times x, to some new variable, a lot of times u. And when you do that, you have to change the variable integration. So we're going to have to algebraically manipulate the dx terms. And so we need to just be aware of what a differential is. And so when we are going to talk now about the chain rule and having the composite function with an inside function times the derivative of the inside, we're actually now going to consider the differential of the inside function, and that's going to allow us to manipulate the variable of integration. So there's a little mini lesson on what it means to be a differential. Don't overthink it. For us right now, if you want to know more information about differentials and what is actually going on in the nitty-gritty mathematics, let me know. I'm more than happy to explain it to you. But for us now, all we need to know for solving these integrals is that differential is another form of kind of like another form of the derivative. dy equals the derivative dx. Okay. Now let's look at this thing called change of variable u substitution. A lot of times we call it u sub for short. U sub. Okay. Here's what you do. If you have some function and the integrand is composite, so like here the integrand is clearly composite, and you have some derivative function evaluated at some inside function times the differential of that inside function, well then you can let the inside function be u and let the differential of the inside function be du, anti-differentiate with respect to u, get the answer, and usually that substitution allows us to make the integrand simpler, but then at the very end we back substitute the original variable, most of the time is x, but not always x. Here's what I mean by that. I know that doesn't give you a lot to go on, so I'll give you an example. All right, suppose we have this. Example 4.2.3. Now, you might be able to use pattern recognition like we did in the previous examples. In fact, you could. Okay, I'd probably use pattern recognition if I was gonna do this problem. But you might not see that immediately, and I understand that. No big deal. Here's what we can do. What if we let the inside function be a new variable u? So let u equal the inside function, 5x minus 2. Okay? So then I can immediately say, all right, just by substitution, I can now work with the antiderivative of u cubed. That's what that implies, right? But here's the problem. I haven't substituted dx yet. And it makes no sense as far as solving the original antiderivative if I have u's and dx's mixed up together. Like if I'm going to change the variable to u, I also have to change the variable of integration to u. That is, I need a du there instead of dx. But I can't just change it to du without a good reason. And so you have to reuse that substitution. So here's what we do. We say, all right, if my substitution is u equals, 5x minus 2, what I do is I find the differential of u. That is, I take the derivative of both sides, and I get du equals what? 5, but I write it in differential form. So if I write this in differential form, I get du, the derivative of u, is 5, the derivative of 5x, times the differential, because that was the variable there on the right-hand side. So here's what I get. I get du equals 5 dx. Okay? And so if I want to replace my dx with du, well, I know not what dx equals, but I know what 5 dx equals. So what if we think about this? I need a 5 right there. So what if I multiply by 5 over 5, and then I pull in the 5 that I need, and now I know that 5 dx equals du. And that's where, on the next line, I now have completely changed over my variables to u. I have a function, an integrand in terms of u, and I have my variable of integration in terms of u. Now, why do we do that? Well, now that's a super easy indefinite integral. It's just a power function. So I can use the power rule, and we increase the power by 1 and divide by that new power. So what? We increase the power by 1, get u to the 4th, and divide by 4. And of course, I have to multiply by that 1/5 out front. So if I simplify that a little bit, I get u to the 4th over 20 plus c. But now we got to be careful here, because that's not our answer. That's our answer almost. But remember, we started with the function in terms of x. Way up here, that function is in terms of x. So I want my answer to be in terms of x also. So what I do is I just reapply the substitution. We call it back substitution. So I know that u equals 5x minus 2. So I replace u with what I know it to be equal to, 5x minus 2. And we get that. That's what's called change of a variable substitution. We changed over to the variable u, and we did so with just a strategic substitution. And we had to do a little bit of algebraic manipulation also, because we also had to change the variable of integration to u also. Okay? If if you are at all unsure, you can always check your solution via differentiation. So here I'm taking the derivative of our answer. Now I left off the plus c just because, well, we know the derivative of c is 0, so we can just forget about it. And what do you get? Okay, well, notice that the 20 there on the bottom, well, that is a constant, and you can factor it out via the constant multiple rule. So there's no need for a quotient rule here. That's overkill. No need. It works, I suppose, but there's no need. Okay, so we factor out a 120, and then we say, oh, you know what? Oh, I need to fix that before. This is missing some notation here, so I need to put a note here. I'll fix it before you see it. This needs to have some derivative notation, d dx, like so. And then we're going to multiply by the, apply the chain rule. So that's the 4 goes out front, 5x minus 2 to the 3rd power times the derivative of the inside function. But the derivative of the inside function is just 5. So we have 1 over 20 times 4 times 5x minus 2 cubed times 5, but 4 times 5 is 20, so we have 20 on the top, 20 on the bottom. They all cancel out, leaving us with just the original integrand. Therefore, we are confirmed that our solution is indeed 5x minus 2 to the 4th power over 20. Okay, so let's look at a couple examples of this change of variable u substitution. Now, usually, not always, usually if we allow the inside function to be our u, the substitution, it'll usually work. Now, as we progress through the class, as we do more harder examples, as you move to Calc 2, that will not always be the case. Sometimes, like if you have a fraction, maybe you let the whole denominator be the substitution, be u. Or maybe you let part of this or part of that. You just have to build an intuition for these things. But it looks like for these first couple examples, C is a little bit harder, but for A and B especially, we're just going to let the inside function be our substitution. So, for example A, just off to the side, this does require scratch work off to the side. Let's let u be the inside function. So that's 3x squared plus 4. Now, here's the thing. As soon as you make your substitution, immediately calculate the differential. That is, what is du? Well, du is the derivative of this right-hand side times dx. So what, that's 6x, I guess? The derivative of 4 is 0, so 6x dx is the differential of u. Okay, and now let's try to plug in what we can. Now, we can say this is the antiderivative of, well, we have 3x squared plus 4, that's u. So we get u squared. But I still have an x right there, and I have a dx right there. So I have x's and u's jumbled up here. That doesn't make any sense. I need to change everything over to u if we're going to do this method called substitution. But what haven't I used yet? I haven't used the differential information that I have about du equals 6x dx. Now watch, I can rearrange these terms because of the commutative property. So I could say that's u squared and then put the x right there. So notice I have an x dx right here. I want a 6 dx. So what if I multiplied by our strategic version of 1 and then moved the 6 on the numerator right there. So now I have a 6x dx, which I know 6x dx is equal to du. And now I can rewrite this as so. So I've changed over completely to a new variable u that's much easier to handle. It's just a power rule. A lot of times whenever if you make the good substitution, what's left over is a very simple problem. U squared has a super easy antiderivative, and it's not composite anymore. So let's see, we have 1/6. What's the antiderivative of u squared? Well, it's a u cubed over 3. We increase the power by 1 and then divided by the new power, of course, plus c. So that gives us what? U cubed over 6 times 3 is 18 plus c. Now just don't forget, that's not our answer, because we want our answer to be in terms of the original variable, which is x. So we back substitute. Instead of u cubed, we're going to say 3x squared plus 4 cubed over 18 plus c. Okay, there we are. Let's check it. Derivative. I'm going to make the executive decision to ignore the c because we know the derivative of c is 0. So we're just going to do the derivative of 3x squared. Oh, that's a terrible 3. 3x squared plus 4 cubed over 18. Okay. Notice we're dividing by a constant 18. That's the same thing as multiplying by 1 over 18. So we can factor out, and now we're left with just a composite function, but no quotient, which is nice. Now, what is the outside function? What's the inside function? The outside function is x cubed. The inside function is 3x squared plus 4. So the chain rule says, well, first of all, we have the 1 over 18. Then the chain rule says we take the derivative of the outside function, 3 times something squared. Second step of the chain rule says you immediately plug in the inside function, 3x squared plus 4. And then the last step of the chain rule is you multiply by the derivative of the inside function, which the derivative of 3x squared plus 4 is 6x. And now if we simplify, notice we have 3 times 6, 18 over 18. Those cancel out. And that leaves us with an x times 3x squared plus 4 squared, which is the original integrand. So yeah, we're right. Nice. Always nice to be right. Sometimes you make mistakes and it doesn't work out so nicely. It's nice whenever you can confirm your solution is indeed correct. And again, I've said this before many times. you should be in the habit of confirming your solutions to antiderivatives. You should be in the habit of confirming those solutions via differentiation. All right, B. Let's see here. I see a radical, but here's the thing. That radical does not fit my inverse trig patterns. Remember, for those inverse trig patterns, you need something like 1 over radical 1 minus x squared, or 1 over x with x squared minus 1. You need those patterns. I don't see squareds anywhere in here. So inverse trig, arc secant, arc sine, not going to help us here. But I think just a good old substitution will help us here. Now, before I do that though, let's rewrite the radical. And this is generally, unless you're going to use inverse trig, a lot of times, not always, but a lot of times it's going to be a very good idea to write your radical so it's not on the denominator, and use exponents, 1/2 powers for a square root. In this case, we're going to use a negative 1/2 power since we want to move that radical to the numerator. So let's just do a algebraic move real fast. This is going to give us 2 times 7z plus 8 to the negative 1/2 power dz. All I've done there is rewrite algebraically its equivalent form. No big deal at all. Okay. Now let's make our substitution. Here, like I said, I think the inside function will do it for us. Let u equal the inside function, which is 7z plus 8. Okay, so immediately take the differential. Du equals what? 7 dz. Okay, du equals the derivative times dz. So the derivative of 7z plus 8 is 7 dz. Now, okay, we start trying to substitute here. We can go ahead and say, all right, 7z plus 8, that's u, so I have u to the negative 1/2 power, but I still have that dz, and I have a 2 there. Well, okay, the 2 is easy to fix, right? I can factor it out. It's a constant, so let's just go ahead and factor that out. The 2 there. Now I need a 7 right there. I need a 7 dz, because if I can get a 7 dz, I can replace that with du, which is how I need to replace to make my variable of integration consistent with the new variable. Okay, so if I need a 7 right there, well, that's just a constant. So what if I multiply, here, let's move this over just a little bit. What if I multiply by 7 over 7? But then, okay, well, if I pull in this 7 on the numerator and put it right there, that'll leave a 1/7 out front. And now I have 7 dz. I know that 7 dz is equal to du. And so now I have successfully changed my variable over to u, and the variable of integration and the variable of the integrand. So now, now I'm good to go. I do have a 2 over 7 out front, but that's just a constant that comes along for the ride. Now, how do you anti-differentiate u to the negative 1/2 power? Well, you just apply the power rule for anti-differentiation. So we increase the power by 1, and then we divide by that new power. Add your plus c. So we have 2 over 7. Now u to the negative 1/2 plus 1, that's u to the positive 1/2. And then we're going to divide by 1/2 plus c. But remember, if you divide by 1/2, that's like multiplying by 2. So if you multiply 2 over 7 by 2, that's 4 over 7 u to the 1/2 plus c. And if we back substitute now, we want to get our final answer in terms of the original variable, which was z. So I write my final answer is 4 over 7. Now u is 7z plus 8 raised to the 1/2 power plus c. There we are. You want to check? Sure. Let's be in the habit. Let's check all three of these. So we can assume the derivative of the c is 0. Now we want to take the derivative with respect to z of 4 over 7, 7z plus 8 to the 1/2 power. Let's factor out the 4 over 7 using the constant multiple rule of differentiation. That leaves us with just 7z plus 8 to the 1/2 power. Now again, we have a composite function. So the outside function is what? It's x to the 1/2 power. Inside function is 7z plus 8. And so let's see what the chain rule tells us. We have the 4 over 7 out front times, okay, we bring the, according to the power rule, the derivative of x to the 1/2 power is 1/2 times something raised to the negative 1/2 power, where we immediately evaluate at the inside function, 7z plus 8. And then we multiply by the derivative of the inside function, 7. So what do we see? Well, we see that we have a 7 there and a 7 there. Those cancel out. We have a 2 there and a 4 there, so that goes to a 2. And that leaves us with what? 2 over 7z plus 8 to the 1/2 power, otherwise known as 2 over the square root of 7z plus 8. It's exactly our original integram. So we were correct. Yeah, we're correct. Cool. One more example. Now this last example is a little more complicated. Not too much more. But when you look at it, notice we have like a doubly composite function. Now, why do I say it's like doubly composite? Because we could say this is equal to the indefinite integral of sine evaluated at 5 theta. Man, 3's and theta, that's what I have trouble writing. 5 theta, but that's squared. The whole thing is squared like so, times cosine of 5 theta, d theta. Now, I think if you write it like that, it's probably good to write it like that, because this kind of tells you what should your substitution be. Your substitution should be the inside function of that quadratic term, the squared term. So let's see what happens if we do that. Now, if you try to make your substitution something else, it might work or might not work. Okay, and if your original substitution, like if you said like the inside function is 5 theta, I wouldn't fault you for saying that, because that's definitely the inside function of something. I don't think it's the right inside function. So if you try to use your substitution and hit a roadblock, well, maybe it was the wrong substitution. Try something else. So I think the substitution should be the inside function of the quadratic term. So that's going to tell me that u equals sine of 5 theta, which is itself a composite function. Now, remember, as soon as you make your substitution where you say u equals something, immediately take the differential. Calculate the differential. So du equals, what's the derivative times d theta? Well, this is composite. So the chain rule says you take the derivative of the outside function, cosine, evaluate at the inside function, 5 theta, and then multiply by the derivative of the inside function, 5. And since this is a differential, we put a d theta on the end, because we're calculating a differential. Now notice we almost have what we need to change over our integral. Okay, let's see here. We could say just right away, we could say this is the integral, the indefinite integral of what? If sine of 5 theta is u, this would just turn to u squared. Now notice the rest of this, we know that du equals cosine 5 theta. Okay, we have a cosine 5 theta times 5 times d theta. We have a d theta too. The only thing we're missing is a 5. If we could put a 5 here, then we could change this entire stuff right here. We could change that over to a du, is what we need to do. So what do? We do that same thing we always do. We multiply by our strategic version of 1, which in this case is going to be 5 over 5. Actually, I'm going to do it right here. Let's do it right there. Save ourselves a little room. Okay? Now, if we put a 5 over 5 there, I can factor in either 5 over 5, I can factor in 1 over 5, I can factor in 5 over 1, and in fact, I'm going to factor in the 5 on the numerator, because if I do that, I can place a constant 5 right there, and now I know I have cosine 5 theta times 5 times d theta, and I know that all of that can be replaced simply by du. And let's not forget the 1/5 out front, that sticks around. So now I have this complicated trig situation. When I make my change of variable, all I have is u squared with the 1/5 out front. That's way simpler. Okay, and then this equals 1/5. All I have to do is anti-differentiate u squared, and of course I get u cubed over 3 plus c. Of course, on the bottom I have 5 times 3, it's 15, so I get 1 over 15 times u cubed plus c. And then our last step is just to change back to the original variable, back substitute, so that reapply our substitution. We know that u equals sine 5 theta. That's at the top left hand of the screen right now. And so we get 1 over 15 sine 5 theta to the third power. Let's see. Cool. Let's check ourselves via differentiation. So let's take the derivative with respect to theta of sine 5 theta cubed. Now we're going to forget about plus c, because we know the derivative of plus c is 0. Now, this is a chain rule. Actually, it doesn't require 2 chain rules. We did an example like this way back about a month or 2 ago. Now let's identify. Oh, well, that's fine. You can see you're just missing barely a little bit. We can first identify the outside and inside. Okay, overall, the outside function, I'll call it theta, is theta cubed. And the bigger inside function is going to be sine 5 theta, like so. So what does the chain rule for differentiation tell us? It says take the derivative of the outside function. That's 3 times something squared. Now the reason I put a blank there is because the next step of the chain rule is to evaluate at the inside function, which I know is sine 5 theta. And then the next step is to multiply by the derivative of the inside function. Now I'm going to not combine steps here because this is going to require another chain rule. So equals 3 times sine 5 theta squared times, okay, now let's update our outside and inside function for the new chain rule. Now looking at oh, where'd my cursor go? There it is. Looking at this derivative, the outside function is sine theta, and the inside function is 5 theta. So if we apply the chain rule, we take the derivative of the outside function, that's cosine. We evaluate at the inside function 5 theta, and then we multiply by the derivative of the inside function 5. Oh, you know what? I left off my 1 over 15. I was about to say, what's happening here? I'm not getting the right answer. It's because, and you might have been screaming at your screen or scratching your head, I left off the 1 over 15. So a 1 over 15 goes there times the derivative with respect to theta, like so. All right, and then that means I need 1 over 15 is a constant. So I have a 1 over 15 out front, times both of those. Equals. Okay, now that makes more sense. Because I I have 1 over 15 times 3 times 5. That's, there's 15. 3 times 5 over 15. And that gives us sine 5 theta squared cosine 5 theta. And if I just rewrite this as sine squared 5 theta cosine 5 theta, that is precisely what I started with. So yes, that was indeed correct. All right, so this is where, I guess say the hard ones for the rest of the class are going to be the ones, the antiderivatives, the indefinite integrals that require substitution. Now, these weren't too bad. Like I said, these basically you can let the inside function be u, and then you got to do your algebraic manipulation to figure out how to rewrite your integrand. But you change over to your new variable, and then you have a simpler antiderivative to work with. The whole point is to make the antiderivative simpler to calculate, and then we back substitute at the end. Okay, they will get more complicated. These take significant practice, so please hear me. I guess I haven't reminded you of my expectation recently. You really have to be spending, on the order of 2+ hours per day studying, and this section will drive that point home. There's some sections you might get away with, oh, this is easy, no big deal at all. But this chapter in particular, this section and then the rest of the chapter is very challenging. It's my favorite chapter. I find it very interesting, but it is very challenging, especially for first-time calc students, first semester calc students. So make sure you're practicing. Make sure you're doing lots of these examples. I'll of course do some more examples in the next video, but make sure you're doing your part. If you do that, then you'll come out the class, you'll finish the class just fine. Okay, I'll see you in the next video. Always feel free to reach out if you need help. See you then.